Now recording. Excellent. Okay. Well, we are here at the end of the class. A couple of pieces of business we need to deal with, and that is, first of all, when you're completely done with your, with your lab equipment, your iLab cars, please make sure you get those back to me. You can take them to a campus. You can take them to one of the MPCC campuses, or you can bring it to North Platte, or you can send it with somebody else who's coming to North Platte, or you can pop it in the mail. If you pop it in the mail and if you pop it in the mail, I should be able to get you a check to reimburse you for the postage that you need to get it here. And yeah, so anyway, I don't think I've ever had anybody actually mail them back to me now that I think about it. So if you want to get reimbursed for postage to mail them back to me when you send them back, just include a note like on the outside, please reimburse for postage. Just write that on the outside of the package or something. So when I get the package, I remember to look into that and figure out how to do that. I'm pretty sure I can do it. I just don't think I've ever done it. So this is all new to me. So today we're going to finish up the chapter on, I think it's, sound and hearing. And then the final exam, which will the final exam that we will take will be this one here, final exam copy, chapters 1 through 17 minus thermo. And so this one does include some stuff, a couple of things from chapter 16, but I'll teach you those things while we're doing the sound and hearing chapter. So we will have homework due Friday. You can take the exam Friday or Saturday, really, if you want to. Make sure that you get all your labs turned in. If you haven't turned those in, get those turned in by Friday so I can grade them. And I will have grades finished up and posted by Saturday evening. And then the class will be over. Second order of business is if there's anybody who needs to take the second semester of this class, then you should, and you want to do it in the fall. We do have one student interested in doing that in the fall, and if I can get 5 students total to do that in the fall, then maybe they'll let me teach it. They'll let me teach it as an independent study course, no matter what. But independent study is not usually all that much fun for the students, so it's better to kind of have people to take the class with. But if any of you need to take the second half of the class and you want to do it in the fall, tell me, and I will try to see if we can find enough students to do that. All right. Excuse me. So let's go ahead. Let's see here. I need to figure something out here. Share screen. All right. I'm going to make toolboxes up here somewhere. Yeah, you can. You can call from my office there if you want. Oh, your phone, okay. Or you can send them an email. All right. Excuse me, sorry, long day. Okay, so chapter 17, which is, I believe, the chapter on sound and hearing. We're skipping chapter 16, but like I said, I'm going to cover a couple of things from chapter 16. we won't necessarily do the homework from chapter 16. That's another thing I gotta fix really quick here. So the only thing that will be due this weekend will be the chapter 17 homework. We'll move chapter 15 out. We'll move chapter 16 out. Just chapter 17 and the final exam copy. So that should fix us all up there. So let's go to chapter 16 and just learn a couple of things, basic stuff about waves, so that you understand what we're talking about when we talk about waves in hearing, in the hearing chapter. When you have waves, they're caused by things vibrating, of course. And this is also things that are vibrating, going back and forth across some kind of equilibrium point. That's also called periodic motion, because the periodic means that it has a period of time that it takes to go through the motion. The amount of time that it takes to go through its complete motion and then start repeating itself is called the period, and we call that capital T. And the inverse of the period, or 1 over the period, is called the frequency. So period, of course, is measured in seconds, and frequency is measured in 1 over seconds, which we call hertz. So 1 over seconds, so it's cycles per second, or per seconds. So that's hertz. So here they do an example of a medical ultrasound in the period of a middle C. Now these two things are of course related to sound, so this is a good example for us. In a medical ultrasound, they use sound that has a period of 0.4 microseconds, so 0.4 times 10 to the minus 6 seconds. And to calculate the frequency of that, we take 1 over this period, 1 over that time. So 1 over 4.4 microseconds, and you get 2.5 times 10 to the 6 hertz, or 2.5 megahertz, 2.5 million hertz. So that's frequency and period and their relationship. For the middle C on a piano, the frequency is 264 hertz. Excuse me. So to find the period, you take 1 over that frequency. 1 over 264 is 3.79 times 10 to the minus 3 seconds. So it's 3.79 milliseconds for each wave of that sound to go by, which is kind of a middle pitched sound, not very high, not very low, right in the middle of musical spectrum. They also in this chapter talk about simple harmonic motion, simple harmonic motion being the very simplest type of wave motion, or oscillating motion, or vibration motion, whatever you want to call it. And if you have, and many things have simple harmonic motion or are related to simple harmonic motion. Here they talk about springs, and so they're able to calculate the period and frequency of a spring in simple harmonic motion, not anything we need to use for the second class. But here you can see simple harmonic motion on a car if it bounces up and down because its shock absorbers aren't working, or a mass on a spring as it bounces up and down in gravity. That's simple harmonic motion, and it makes this wave. And simple harmonic motion creates a wave that is easily modeled with a sine wave or a cosine wave. So that's something that they show us here, and this is something that we will see a little bit of in the sound section, I believe. And that is the form, the mathematical form of a wave. When you have a wave, when you have a waveform like this that is represented by an equation, the number in front of the cosine function tells you how big the wave is, how tall it is, from its center point to its highest height, or the center point to its lowest point. And that's this number here, and it's called the amplitude. When it comes to sound, the amplitude is equivalent to the loudness of the sound, or I guess not loudness, but the intensity of the sound, I suppose. But it is the loudness, pretty much, like the volume of the sound. So as this number gets bigger, the wave gets bigger, and the sound would get louder. These numbers over here, the 2 and the pi are part of rotational motion kind of thing. The T is just how much time has gone by, and then this big T down here is, of course, the period again. And because the period is equal to 1 over the frequency, you can actually rewrite this equation with frequency in it. And that is something we will see a little bit in the next chapter, so we want a little bit of introduction to that. Then they talk about the pendulum. The pendulum is interesting because a pendulum has a frequency that it's dependent on its length. It doesn't care what kind of weight you put on the end of it. It only cares how long the string is, as long as it only swings a little bit. And that's why they use pendulums in clocks, in old clocks, for example. So that's an interesting one. We won't go into the details, but if you want to know more details, you can go ahead and look at them. And then the last one here, they talk about the energy that is in a wave, the energy that is being carried by a wave. And energy in waves can be both potential and kinetic. The movement part of the wave can be kinetic, but the thing that's causing the movement can be a potential energy. So it all plays into the conservation of energy kinds of things. And we will deal with this a little bit differently when we go to sound, but it is something we will talk about a little bit. And then they talk about uniform circular motion and how it relates to simple harmonic motion. And this is actually how the whole idea of the sine and the cosine function came about. And again, not something we're going to do in our homework for chapter 17, but it turns out to be useful to understand that this comes from circular motion eventually. And then damped harmonic motion versus I just blanked on the word. So with damped harmonic motion, what you have is forces that are slowing down the motion or causing it to get causing the amplitude to decrease. In this case, they show you a damped oscillation, on a damped harmonic motion where it's going up, down, but it's going up and down a little bit less, a little bit less. Eventually it'll just disappear. And that's the idea of damped motion. And this happens in sound also, but we're mostly going to talk about sound in terms of resonating sound waves, which are more interesting for sound in general. So we'll talk, and that's kind of like the exact opposite of damped motion. It's motion or waves that get bigger because of the circumstances they're in. And so we're gonna talk about this, but it'll be we'll be talking about the opposite of it essentially. And that's chapter 16. Oh no, here's the last one, chapter 16 actually. In this one they do talk about resonance, and so that's the one that we will talk about in sound. So why do we talk about resonance and not damping in sound? Damping is important in sound because sound always gets damped out over time, depending on the situation that you're in. How it damps out, you can either choose that or you have to study your surroundings and see how it's just going to be damped out naturally. But for the most part in music, we're trying to take a small vibration, like a vibration in a piano string here, and make it really big so that it sounds louder, but not only louder, but it also sounds more full. And we do that by amplifying not only the vibration, the main vibration in the string, but other vibrations that happen in the string. Because whenever you pluck a string or you hammer something, hit a drum with a drumstick or something like that, it doesn't just create one kind of vibration. It creates many kinds of vibrations in whatever it is that you perturbed, whatever the string that you pulled or whatever. And all those vibrations have different wavelengths and different frequencies. And what you're trying to do with music, for example, is you're trying to amplify certain waves, and you're trying to not amplify other waves. And the waves that you amplify give the instrument that you're playing the character that it has. That's why a piano sounds different from a trumpet, because a piano amplifies different waves than a trumpet does. So they sound very different from each other. People's voices have more, you can always tell when somebody's voice has a lot of resonance and a lot of tones in it are being amplified because they have a very rich sound to their voice. So James Earl Jones, for example, the voice of Darth Vader, You know, has a very distinctive, deep resonance voice. Kathleen Battle, the famous opera singer, she has an incredibly rich voice, considering especially how high she sings. You know, so their voices they resonate by doing certain things with their mouth and throat, and just natural things that are already there in their bodies. So it's that's kind of what we're going for, and this resonance happens essentially because of situation. Here's an example where you can see resonance. You can actually bounce a ball on the end of a bouncy string. You ever played one of those toys where you have the paddle and the ball, and you try to hit the ball with the paddle, but the ball is connected to the paddle, so it always bounces back? Those are really hard to do because you have to get the paddle going at just the right speed, at just the right frequency, back and forth, back and forth. If you don't do that, the ball doesn't really bounce back and forth very well. It's just messy. And it has to be the same speed every time. You can't just pick your speed and go. There are a couple of different frequencies that will work, but usually the only one that is practical to use is the one that you can actually, I mean, the other ones are too fast to move to. Anyway, the point being is that there are certain frequencies that you can resonate at because of the length of the string or the mass of the ball or other things like that. If you've ever jumped rope, played jump rope, you know that, and you have two people swinging the jump rope, if one person swings at a different speed than the other person swings, it doesn't make a nice big wave. It doesn't make a nice big rope to jump. And that's another type of resonance where you have two things creating a wave in a rope, two people creating a wave in a rope. And if they're not in sync with each other, that wave doesn't grow to be big. There are many examples of this where, for example, when you're swinging on a swing, as you're pushing somebody on a swing and they come back, if you push them at the wrong time, you'll just push them out of the swing. But if you push them at just the right time, which is right after they've stopped and they start going forward again, and you push along with their motion, then they swing even bigger than they did last time. But if you swing as they're coming towards you, they're moving towards you, and you push them, they'll just fall out of the swing, or you'll slow them down or something like that. You have to push them at just the right time. If you wait too long and they're taken off, then you push and you miss them, and you don't really add anything to their swing. So it has to do with it has to do with the situations a lot, the situation of what's driving the oscillation, what's causing the thing to vibrate, if it's some kind of a force or some kind of situation. People who are familiar with jump roping, really familiar with it, know, for example, that if you have a very lightweight jump rope, you have to swing it faster. So the weight of the rope can make a difference. The length of the rope can make a difference. A longer rope usually has to be swung slower when you're jump roping. If you have a really, really heavy rope, it has to be swung slower for you to jump rope. And that's because if you try to do it too quickly, the weight of the rope can't make it around. The system won't allow it to happen. There's just a lot of things that can affect resonance in the system. And resonance being that sweet spot where everything works out well and the wave gets big. The wave just gets really, really big. How many of you have been in a swimming pool and you've been in like inner tubes and you start bouncing the water up and down? Have you ever done that in a swimming pool before? And if you get it just right, you can make huge waves. In fact, they do this in wave pools all the time. Wave pools are essentially just a swimming pool that has a big wall that's pushing the water back and forth. And if you push the water, allow it to go out to the other side of the pool, and then when it comes back and bounces off the pushing wall and is moving out again, if you move that pushing wall again right at the right time, it'll make the wave bigger, and then bigger and bigger and bigger, and you can make huge waves if you push it just the right time for the length of the pool and the movement of the water. So it's all about the conditions and the situation and the geometries and all the things like that affect how this resonance thing happens. And if everything works out just right, you can get things to resonate and you can create big waves. And you can do that with sound. Sound is the way that you do that with sound usually is by letting the sound bounce inside of some kind of a box that is the same length as the wave-ish. So that as the wave bounces back and forth, it builds on itself when it bounces back. It bounces back and builds up on the wave that was bouncing forward. and the wave gets bigger and bigger and bigger. So it makes a nice loud sound. If you've ever plucked a string that doesn't have a guitar box on it, you know it doesn't make much sound, but if you put it on a guitar box, it makes a lot of sound because the guitar box is designed to be just the right size to resonate with the waves coming off of that string. And you notice that the guitar box is shaped funny. You know, guitar boxes are shaped like this. You ever wondered why a guitar is shaped like a peanut? Well, the reason the guitar box is shaped like a peanut is because the however many strings you have on your guitar, it could be, you can have as few as 4 for a ukulele, or you could have as many as 12 for a 12-string guitar. But I think that's the biggest I've ever heard of. But anyway, whatever number of strings you have, each one of those strings has different vibrations it makes, different waves it makes. And the really thin strings that are really tight make really tiny waves. And so this spot right here that is the tiniest spot is measured to be about the size of those waves. This spot here that goes from corner to corner is the biggest wave spot, designed for the lowest strings, the loosest strings. And so that you can get resonances of all sizes. And you can see with this funny shape, you can get just about any length of wave in here to resonate. So you have a lot of resonant possibilities. Electric guitars do a completely different thing. They use metal strings, and the metal creates a current in a little pickup, and that current is carried to a speaker, and then it's played on a speaker. So if you turn off if you unplug an electric guitar, it has no sound to it. Essentially, it doesn't sound like anything, unless it's like an acoustic electric guitar, like those arch top guitars or whatever. But anyway, so that is what they're talking about here, is this idea of oscillations resonating and getting bigger. This is kind of a cool story that from the 40s. The Tacoma Narrows Bridge was built, and just a few short years after it was built, actually I think it was a few short months after it opened, it actually collapsed because of resonant waves that were building up in the bridge. Let's see if I can find my, there we go. So while they were building, hold on a second. There we go. So while they were building the bridge, they noticed that there was a little bit of sway in the bridge. It was swinging back and forth just a little bit. And they figured, oh, it's just the wind blowing a little bit, it'll be fine. But then by the time it was finished, this is what was happening to the bridge. They only allowed traffic across it for a very short amount of time because the bridge was vibrating so badly. And you can see here that it's not just going up and down, it's got a twist to it. And it was actually kind of a joke that kids like to do. They like to race across the bridge and see if they could make it across. But by the time it was doing this, that bridge is moving like 25, 35 feet up and down on each side. So they had closed it by then. And what they discovered was that this bridge was just, oh, and this is a funny story. There was a professor that was doing some studies on the bridge because they were trying to figure out what they did wrong. So he drove his car out to make some measurements, and then he couldn't get it off the bridge. So he ended up actually walking out onto the bridge. You can see his car right there. But he ended up walking out onto the bridge to remove his dog because his dog was in the car. Right here you can actually see though that the line on the center of the bridge is not moving very much. So he could actually walk on that line, and the bridge was like tilting back and forth on either side of him, and he just walked out right on the line out there and grabbed his dog out and then walked back and made it. But what they discovered was this area has wind, but not that much wind. I mean, it's not a huge amount of wind. But what they discovered is that the bridge was just the right length and at just the right angle and just the right shape, that any amount of wind coming down there would cause it to vibrate a little bit. And it was just the right amount of wind pretty regularly that it was kind of like pushing somebody on a swing. Every moment of every day, there was just a little bit more push that was causing this bridge to twist because it was just the right length in just the right place. It was just perfectly built in the wrong way. And over a few months, this grew from, a few millimeters of movement to meters and meters of movement, to 10 meters of movement. You can even see the cables. You can see the cables moving here. That's not supposed to happen. And eventually it got so bad, there you can see the car on the bridge a little bit better. And here you can actually see the professor walking on the line of the bridge, right there. So he's coming back with his dog. So anyway, it's totally crazy. But eventually, it did just fall apart. Now, after studying that for all those years not all those years, all those months, they studied it and studied and studied it. They did rebuild the bridge in a different place with a different design so that it wouldn't have this problem. And that bridge still stands today. But other structures also have this problem. Like the biggest building I've ever been in, I think, was the Transamerica building in San Francisco, which used to be the biggest building in San Francisco. Now it's not anymore. There are several buildings bigger than it. But I think it had 40 stories or 42 stories or something like this. So at the top of that building at 42 stories, there is actually a little bit of movement to that building at the top that you can feel. And other buildings that are that tall, 20 stories, 30 stories, 40 stories, you can actually detect movement. You get up into that tall building and you'll sight along the edge of a window pane or something and watch another building, and you can actually see movement between the building you're in and the building that you're looking at, or whatever it is you're looking at. And so when this happened, people started to think more about, these really tall structures. Now, when you build they built a bridge like this, a suspension bridge in Japan 20 years ago that I think is still the tallest suspension bridge built in the world. The towers are 1,000 feet tall, and and the bridge is like 2 miles long, which is almost twice the size of the Golden Gate Bridge. Actually, I think it's more than twice the size of the Golden Gate Bridge. So it's a huge span. And halfway up those towers, they actually put a pendulum in each tower that's hidden in the tower. You can't see it, but it's a big pendulum. So that as those towers kind of sway back and forth, the pendulum sways the other way. It swings the other way. And it actually counteracts the swing. It dampens the swing to keep it. Because if they start swaying and then something causes them to resonate, it would just break it in half. So you need to take out that resonance. And they do that in big buildings too. In big buildings that are, 40 stories and taller these days, they have an entire floor that's completely empty. There's nothing there except big masses on wheels. So that as the building vibrates back and forth and sways and everything else, these masses move the other direction and dampen that out. They stop that resonance from happening. They essentially prevent resonance by creating damping in the building so that you don't create these kinds of problems with the waves in the buildings. Now, of course, this is kind of the opposite of what we want with music. With music, we want resonance. We want that big wave, right? You don't always get it, but you want it. And this is why instruments are made the way. A good example of an instrument that is made for resonance is the instrument I play, which is the trumpet. So a modern trumpet today looks like this. Actually, this is a nice picture here. So it's got all these parts to it in a modern trumpet. And each one of these parts is designed to give the trumpet a different length if you put down a different combination of keys. And that different length resonates with a different wave. Okay? Now, old trumpets, you could go back If you go back to ancient days, this is what your trumpet looked like. Whoa. Or maybe this, if you were, this is like the trumpets that they played at the Battle of Jericho, for example, the Yemenites. They're essentially just a horn from an animal that's been hollowed out, and you just blow through it, and there's nothing to make it any different length, but they could still play a lot of different notes on them, but they didn't resonate very well. So some notes were quieter than others. In the Baroque period, which was the time when Bach was composing music, Johann Sebastian Bach, this is what a trumpet looked like. It didn't have any valves or anything, but they poked some holes in it, and you can see this trumpet player has his fingers on some holes here, and those holes would give it a little bit different resonance. It wasn't much, but it was enough to play a few more notes. But it was much harder to play a Baroque trumpet because of those. To make it play a certain note, you'd have to like force it with your lungs and your lips and everything else, and it was very difficult to do. And trumpet players back then had actually a very short lifespan because their lungs had a tendency to collapse from all the work they had to do to play their trumpets. So, an interesting thing there. But many instruments over time have evolved to create more resonances. The violin, for example, has that same peanut shape, even more so than a guitar. But violins and guitars, at the very beginning of violins and guitars, were more squarish. They were easy to make that way, but they didn't sound as good. Pianos are the same way. A piano has this shape to it that looks like, let's actually go to my whiteboard here. That didn't work. I don't know what I just did. There we go. So a piano has this kind of a shape to it, right? And that is essentially the box of the piano for resonance. And this shortest space here is where the highest notes resonate, and the longest length, which is right here, all the way across here, is the longest length that it resonates in. And the strings are also they're also strung in here to make as much room for longer strings for lower notes and shorter strings for higher notes. And that's how it resonates. It can resonate in lots of different ways. It also is designed to resonate in many different ways. You can close the piano, you can open the piano partially, you can open it all the way. And it also has a sounding board in here, which is essentially a big piece of brassy copper stuff that creates more resonances besides. It has holes in it and all kinds of shape to it. So, but pianos, when they were first being made, looked more like this. The pianoforte, for example, looked like this, which still has different lengths of the piano to resonate in, but it's not as smooth. And so this one had a little harsher sound. It chose specific frequencies, whereas this one pretty much resonates all of the frequencies. So that resonance, that building up of the wave because of the situation the wave is in, turns out to be quite important with sound and music and other things. Let's see here. So now that's pretty much all the stuff that we need to understand, I think, from chapter 16. Let's move on to chapter 17 so that you can do your homework and do the test. So the physics of hearing, sound. Here they have this great picture of a glass being shattered by a high intensity sound with a high frequency. You always see you always hear the story of somebody singing a really high note and it breaking the glass. And it has been done. It can be done. It's not unheard of. In fact, you can watch YouTube videos of people doing it. You have to hit just the right frequency. Why do you have to hit just the right frequency? Well, for the same reason as resonance in general that we've been talking about. In the glass, you start off with like a wine glass or something. Looks like this. Right? And as the wave comes in, as the sound wave comes in, it creates vibrations in the glass. Now, if the vibrations are if the wave of the sound is about the same as the length around the top of the glass, then that wave will start waving the glass, essentially. It'll start vibrating the glass. And when it goes around, it will build up on itself. And as it builds up on itself, it'll vibrate the glass more and more and more, just like pushing the swing or making the bridge go more and more and more. And it'll eventually vibrate it so much that it just shatters. And it's not even that hard to do, actually. Let's actually watch somebody do it, because it's kind of fun. There's this great video of a kid doing this, and it's funny because it almost scares him when he does it. Let's see if I can move that thing out of my way. There we go. So let's go to YouTube. Several people have done it. This is my favorite one, though. So when you do this, a lot of people will put a straw in the glass. The reason that they put the straw in the glass is because when the glass starts to vibrate, it'll actually move the straw. And so you can see when the straw starts to move, you change the pitch of your voice until you see the straw move, and then you keep that pitch and you get louder until it breaks. And so this kid uses that trick here.
Chase, and I live in California, and I'm gonna try to break this wine glass by holding my voice.
They obviously have some animals in their house. He's pretty serious about this. So you can see he's almost got it. That's about the right tone, about the right pitch. The straw started moving.
Mom, I broke it! Look it! I did! I broke the glass!
I thought that was funny. His mom's like, no, you didn't. But he totally did.
That's cool.
It's pretty funny. So anyway, resonance, that's a fun part of this chapter. How are we going to create these waves that we call sound waves? And what are these waves? What are sound waves? Well, one of the simplest ways all sound waves actually are created by an object moving in a medium somehow and vibrating in a medium. The medium that we usually think of as air, because that's the medium that we live in. And so we start off with a string, a very simple moving object. It's just going to go back and forth like you've plucked a string on a guitar, and it just vibrates back and forth. As it goes one direction, it pushes into the air and creates a compression of air. And you think the string's not very big. It can't create that big of a compression. Well, that's why you have the resonant box of the guitar, is it will take that tiny little wave and make it a big sound. But it creates a tiny compression of air this way, but it leaves in its path behind it a rarefaction. In other words, it creates a low pressure region here and a high pressure region here. And then as it moves back this way, it makes a low pressure region here and a high pressure region here. And it goes back and forth doing that. Well, this compression over here will actually create a low pressure region out here as well. So this thing is going to actually propagate outward. As you create this vibration and this high pressure, low pressure thing near the string, that high pressure, low pressure thing will travel outward in every direction away from the string. And that's what sound is. Sound is a wave of pressure, high pressure and low pressure, high pressure, low pressure, high pressure, low pressure, created by an object that is actually moving in the medium and creating that compression and low compression. So back and forth, and eventually you get these waves of high, low, high, low, high, low pressure out there. And if you graphed that as pressure, you'd get high, low, high, low, high, low, high, low like this. over the space away from the string. When that high pressure, low pressure reaches your ear, inside your ear you have your eardrum, right? Your ear is also shaped funny. It's got this big part on the outside, and then it has this, it gets smaller and smaller and smaller, and it's actually a resonant chamber, kind of like a guitar. It actually amplifies, it catches a lot of pressure because the ears are big on the outside, but it also amplifies sounds so that once they get to your eardrum, you can actually hear them. So anyway, this sound wave comes into your ear, high pressure, low pressure, and as it encounters this membrane, which is your eardrum, the high pressure pushes that eardrum in. It stretches it in. And connected to the back of the eardrum is a little bone called the hammer. It's one of your inner ear bones. And it actually hits a little thing called the anvil, or rotates on it or something. But eventually this movement that are on these I think it's 3 little bones in your ear, they're the smallest bones in your body, this movement eventually knocks on your auditory nerve. It actually hits your auditory nerve and creates impulses, electrical impulses along your auditory nerve, which go to your brain. And your brain says, oh, that's hitting this fast. That's a high sounding note, or it's a high sounding voice. You know, it depends, the quickness of that repeating pressure wave coming into your ear and that tapping on your auditory nerve is interpreted by your brain as sound, essentially. Low sound, high sound. Loud sound is harder tapping. Quiet sounds are much less harder tapping, less difficult tapping. And it's a really complicated thing because it's not just one frequency coming into your ear all the time. You have gazillions of frequencies coming into your ears all the time, and your brain can process them all. And the sounds that you hear all the time, your brain just kind of filters them out. Your brain just says, oh, I hear that all the time, I'm just going to ignore it. And this is why parents can sit around and ignore their crying children, because they just get used to it and they can tune it out. And this is why most people can tune out an air conditioner, or can tune out traffic noise if they live near a highway or something like that. You hear all those frequencies and all those sounds, all those pressures go into your ear, and your eardrum moves all the time, and the bones are hammering on your auditory nerve, and there's signals going down your auditory nerve to your brain. But at the end of your brain says, what's different about this? Is there anything I need to be worried about? Anything I'm expecting? Anything I want to know about? Anything interesting? And it kind of sorts it all out, and then it tells the logic center of your brain, hey, look, somebody's honking a horn at you, wake up, right? So that's the basic idea there. And because you have multiple waves traveling, you actually get a really interesting situation often. So this is a simulation of what we call a wave tank. You have 2 faucets here, which we're going to drop drops of water into this tank of water here. And each drop of water is going to create a wave that's going to move outward. You can think of this wave as the high pressure part of a sound wave or something like this. So here we'll start this one, drop, creates this, so that black region, or maybe the blue region, is the high pressure, the black is the low pressure, whatever you want to say. And you can say, so this is high, low, high, low, high, low, high, low. And I can increase the frequency if I allow more drops to drop per second. Then you can see that these things are coming out more often. We're getting waves that are closer together. If you drop them less often, then the waves are further apart, moving out more slowly, right? So that's changing the frequency of the wave. You can also change the amplitude of the wave. It'll change the size of the drop. If I go down to a smaller drop, that'll change how big the pressure changes. So this is not as loud of a sound, for example, right? But you can also get really interesting things like this. Start a new drop. So now I have 2 drops dropping at the same time, and the waves start to overlap each other. And sometimes you're going to get the high pressure part of the wave overlapping another high pressure part. And when two high pressure parts overlap, you're going to get a big high pressure part, like here and here and here. But sometimes a high pressure part is going to overlap a low pressure part, and it's going to go to zero. And that's what's happening right here. This was the color of the tank before I dropped any water in it, and this one here is essentially like a neutral. There's no wave here. There's no sound here. Out here there's sound. In the middle there's sound. Over here there's sound. But on these two lines, right down here and right down here, there's no sound. And that's where a peak of one wave is overlapping with the trough of the other wave, and they essentially just cancel each other out. And that happens with sound all the time. This is why at concerts there are certain seats that are better than others. You definitely don't want to be on one of these lines at a concert. That's also why at a concert they don't just have two speakers. Have you ever been to a rock concert before? Rock concerts look like this. Oops, that's not what I'm looking for. I'm searching the wrong spot. Need to search Google for that. There we go. So if you go to a rock concert, instead of having just two speakers or two sources of waves, they'll have like 500 sources of waves. This is what they call the wall of sound at the Grateful Dead concert, right? This is not just to make the concert louder. It does do that. But they actually have engineers that design this so that you have the fewest possible dead spots in the audience. So they look for dead spots and then they add more speakers, and then they look for dead spots and add more speakers that are pointing into those dead spots to try to get rid of those dead spots. You can never be perfect, but you can always improve things. It starts to get a little bit crazy. So this is what it would look like with sound. So speakers create sound by pushing this cone forward and backwards and creating high pressure, low pressure, high pressure, low pressure. So if I start this one, it's pushing outward, creating high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. Start this one, high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. And you can see where it overlaps. You can see where the high points overlap, those are the white bars. Where the low points overlap, those are the dark bars, and then where the high parts overlap the low parts is kind of the in-between ones, the gray line here and the gray line here, right? And so these two kinds of interference are called constructive interference. When the waves are building on top of each other to make a bigger wave, that's constructive interference. And when they cancel each other out because the peak overlaps a trough, it's called destructive interference. Now, sounds are a compression wave, and a compression wave is a pressure wave. That's a little bit different than a wave on a string, really, because a wave on a string is what we call a transverse wave. A transverse wave is the wave on a string waves in the different direction than the wave moves. So if you have a string like this, and you just lift it up and down here really quick, give it a little bit of a whip, then you'll have a wave that'll travel like this through the string, and it's waving this way, it's waving up and down this way, but it's moving this way. And so this is called a transverse wave because trans means across, verse means movement. So transverse means across the movement. This wave waves, transverse, yeah. This wave does its waving in a 90-degree angle to the way it's moving. But a compression wave is a wave that waves in the same direction that it moves. Well, what does that look like? Well, that looks like, for example, if you have a slinky, and I do have a slinky. All physics teachers have a slinky. My slinky is like 30 feet long. So I probably won't use the slinky because it would be a little awkward, but I can use this spring here. So a compression wave is like this, where you have, let me put my camera up for everybody here, so you can all see what I'm doing here. Stop share. So a compression wave is what happens when you have a spring like this, and on this side where my fingers are grabbing here, I'm going to stretch it this way and I'm going to let it go. And you can see that it goes, there's a wave that goes back and forth in the spring this way. It's traveling this way, but the spring is also compressing back and forth this way, because I pulled it tight and then I let it go, and so it goes back and forth. It kind of zzz back and forth through the spring. That's a compression wave, also called a longitudinal wave. Longi means along the length of, and tudinal means essentially waving along the length of. So it's moving in the same direction that it's waving. And sound is that kind of a wave, because you have something that pushes on the air, but the wave travels in the same direction that you pushed on the air. So longitudinal waves and transverse waves, two different kinds of waves. The speed of a wave can be calculated by using the frequency of the wave and the wavelength of the wave. The frequency, of course, being measured in hertz, 1/2, and the wavelength being measured in meters gives us the correct units, meters per second. So if you know the frequency and the wavelength of a wave, then you can go ahead and calculate the speed of the wave. And that's true for all waves, not just sound waves. Here is a tool called a tuning fork. You may or may not have encountered one of these in your lifetime. I have one around here somewhere, but it's probably in the back room or in one of my cabinets here. I don't know where. But anyway, a tuning fork is just essentially a fork of metal that you hit on something and cause it to vibrate. And the length of the tines determines how fast it vibrates and what kind of tone it puts out. So if you want a middle C tuning fork, a middle C tuning fork's about 6-8 inches long or so, and you hit it on the table and it goes brrr, makes that sound. And what it's doing is it's pressing on the air and creating that compression wave. The compression wave doesn't travel straight away from the tuning fork. It actually travels out in this cone-shaped kind of wave mostly, but it does travel in every direction. This only shows 2 dimensions. It travels in a big cylinder around the tuning fork in every direction, that kind of weird 2-dimensional, 3-dimensional cone-shaped kind of thing. It doesn't travel directly up from here because the top of these are not pressing on the air up here, and it also doesn't travel directly down from here. But it's mostly just these cone shapes that move outward. You can still hear it up here because you hear this wave. But that is that. And the speed of sound, the speed of this pressure wave, remains the same as long as you're in the same material at the same temperature. Once you start changing and pressure, you have to have the same temperature and pressure of the material that you're in. So in air, sound at like the level that we live at, the Earth's level of the Earth. If you're way above the Earth, it changes, but at about the surface of the Earth, it's at about 330 meters per second is the speed of sound. If you go higher, the speed of sound increases. I think it increases as the pressure decreases. I think that's how it goes. As the temperature increases, it also increases. So temperature increases, it increases. Pressure decreases, it increases. But in carbon dioxide, you can see that it's actually slower. Oxygen is slower. Why would it be slower in these things? Well, the pressure in air is caused by squeezing the air closer together, so the atoms in the air or the molecules in the air get closer together, right? So if you have sound that's creating pressure in the air and then releasing that pressure, then there's movement of the atoms. Atoms that are heavier or molecules that are heavier are going to move differently than atoms that are lighter. They're going to have a different kind of thing. And also atoms, there's just a lot of things going on with them. And so it turns out that every gas is different. And it's not just the mass of the gases. It's also every gas has an average velocity at these, like the molecules have an average velocity at these different temperatures, which we just talked about in the last chapter that we did, which was that the temperature, the kinetic theory of gases that we talked about, where you can calculate the speed of the gas molecules. Well, each different molecule has its different velocity, and that affects things pretty dramatically. Trying to think exactly, if I remember exactly how it goes. I think so smaller molecules and smaller atoms in gases tend to have a slower speed of sound. I think that the reason for that is because they have a much higher velocity, and so when you apply a pressure to them in a pressure wave, it's more difficult to kind of apply. Remember, if you go back to the chapter before, the Bernoulli law chapter, which was this previous chapter, when you have higher speed gases, you get lower pressures, right? And so it's a very complicated thing, but the lower pressure, because of the higher average speed of the molecules, which is more of like a molecular pressure, creates a kind of a weird situation where you're trying to apply a pressure to something that has naturally a lower pressure. The details of that aren't important to you. You just need to look at the chart and say, hey, look, hydrogen has a very, very, it's actually higher speed, not lower speed, but it has a much higher speed, and these ones have a lower speed, and it has something to do with the make of the gas, what the gases are made of or whatever. Liquids and solids are very strange here. So liquids generally are higher, but there are some that can be lower. Solids, it depends on what it's made of a lot. Rubber has a really low speed of sound, which means sound just doesn't travel through rubber very well. That's why we use, lots of rubbery kind of things to block sound. Foam is used to block sound, for example. Whereas harder things that have kind of more density to them, sound travels really fast through. Sound travels extremely quickly through steel, for example. So this equation here you can use to calculate the velocity of a sound wave if you change the temperature from 0 degrees Celsius, which would be 273 Kelvin. So if you move it up to room temperature, which is about 300 Kelvin, then you put 300 in place of the temperature here and use this equation to calculate the new speed of sound at room temperature. The speed of sound at 0 degrees Celsius is 331. And of course, this is the equation that we got from the last chapter we studied, where you can calculate the average velocity of the particles in the gas, and that's the thing that affects the movement of sound through the particles. I'm trying to remember exactly. I think I actually got it wrong when I was explaining it just a minute ago, because I think it's actually faster moving particles, faster moving sound, but it doesn't really matter. You just look here, because I think in this case, so the hydrogen is the helium is the smallest particle here. Hydrogen gas ends up with, so it's not necessarily true. Helium is smaller, but hydrogen is lighter. Hydrogen has a smaller mass, but helium is a smaller. So it would be true. So the smallest mass has the highest speed of sound. And this one is almost the speed of sound of like ethanol, which is like alcohol, or water. So it's very close to the speed of sound of water, but this is a gas. But you just need to, kind of look it up. Don't really need to know the reasons for it. Excuse me. An interesting thing about sound is that when you send it out from your mouth, right, as I'm talking, it bounces off of things and comes back, and you can hear yourself that way. That's one of the ways we hear ourselves. The other way that we hear ourselves is that as we make sound in our throat, it travels through our human tissue, our bones and our skin and all that, and it travels up to our ears that way. And so our ears detect our own sound through our own tissue. People who are deaf are really confused by this sometimes, because people who are truly deaf, their ears are not connected to their auditory nerve, they they get a very different sensation through their heads of sound. They can feel vibrations in their heads through sound sometimes. Some of them can, some of them can't. But it doesn't feel like ours does, because we can both hear it and feel it in our heads. So when deaf people, get a cochlear implant or something like that, sometimes it's really confusing for them. They often turn it on for a little bit every day until they get used to it, or turn it off when it's getting annoying until they can really just kind of get their brain used to feeling those vibrations. We take it for granted. We take it for granted until we hear our own voice played back to us. Isn't that always a weird thing when you hear yourself speak? Because when you hear yourself through your skin, your voice usually sounds a little bit higher, has more higher tones to it. And when you hear yourself from a speaker, it usually sounds a little lower because of the speed of the sound changing. It's faster moving through your bones and skin than moving through the air. So it's kind of a weird thing. It creates a different tone to your voice. You never really recognize your own voice when it's played back to you. Bats use this idea of sound going off and bouncing off of things and coming back to them to actually navigate. So a bat sends out these high frequency sounds that we can't even hear, and they send them out, and because they're high frequency, the waves are really small. And these really small waves can bounce off of really small things like bugs in the air. And so this bat sends out this small sound, and some of that sound bounces back off of the bug and comes back, and the bat knows where that sound is coming from. And so it can steer itself towards the bug without anything but the sound, which is good because bats can't see out their eyes very well. The other thing that bats can do is they can tell how fast the bug is moving and what direction it's moving in. Because as the bug moves towards them, it bounces the sound back more quickly, which changes actually the frequency of the sound. So it sounds different to the bat, and they say, oh, that bug's coming towards me. Or if it's moving away from them, it bounces it back more slowly, and the bat says, oh, it's moving slowly. And even if it's moving to the side, if it's moving parallel or perpendicular to these, the movement of this wave, or parallel to these wave fronts, it'll actually make no difference to the frequency, and so the bat will know that it's not moving forward or backward, but it might be moving sideways. So the bat actually can figure all of that out. In fact, we're actually not bad at that either. Our ears can detect things like that, but not usually from our own voice. Usually it has to be from external sound. So if you close your eyes, you can actually tell where somebody is when they talk to you because you have two ears. And if it's louder in your left ear than your right ear, your brain knows that they're off to the left. And you can actually be fairly accurate. With your eyes closed, you can point at somebody who's speaking and be almost perfectly accurate. And it even works up and down to a fair degree and backwards to a fair degree. What doesn't work for us is yelling out all the time and seeing how our voice bounces off of something. We're not designed to do that. But we can take advantage of other sounds that are moving towards us and away from us. And we'll talk about this a little bit later, but you know what it sounds like when a car is moving towards you and away from you. It has this kind of sound, and that's because of this same effect that bats use, which again we'll learn about here a little bit later. Our hearing, the range that we hear in frequency goes from about 20 hertz to about 20,000 hertz. 20 hertz is a very low sound. Let's try to play a 20 hertz sound for you really quick.
Stop taking your generic multivitamin.
Oh,
I'm gonna fill
go
you in
away.
on a little not so secret. Most
I'm pretty sure I won't even be able to register it on these speakers. Can you hear that? Can anybody else hear that? Can anybody hear it at all out there? It just sounds like a bunch of brrrr. Sounds like 20, it sounds like 20 little taps on a drum per second or something like that. That's about as low as we can hear a frequency. It doesn't even sound like a tone to us because all you're hearing is the peak of that pressure wave flying by 20 times every second. And if you go to 10 hertz, it's much more, it has a much more tonal quality. Not 10 hertz, let's go to 40 hertz. 40 hertz is an octave above that. It has a much more tonal quality to it. We have to turn the sound way down because, or the volume way down because this is going to be much louder. Should be anyway. Maybe. Maybe. There we go. Can you guys hear that one?
Yeah, I can hear it.
Yeah. So that's a 40 hertz tone, which means there's 40 pressure waves per second being created, and that's what it sounds like to our ear. 40 hertz. Now, if we go to 80 hertz, every time you double your frequency, you go up one octave in musical terms. So this one we'll have to turn the volume down for because this one should be pretty strong, pretty loud now. Maybe not. So it's never as loud as they think it's going to be. But there's your 80 hertz. And that's definitely within, an easy range of hearing.
Braxton was diagnosed with choroid plexus carcinoma, a brain tumor. St. Jude is helping us.
There's your 160 hertz. And you can go all the way up to 20,000 hertz. The range that we hear the best is kind of right in the middle. If we go up to maybe 400 hertz, for example. So that's actually at the same level of sound. It has the same intensity as all those other sounds, but our ears detect it better. It resonates in our ear better, so we hear it louder. It sounds louder to us, but it's not any louder. This up here actually tells us the loudness, and it's been at -3 dB the whole time. So all of these sounds have been the same loudness, just different frequencies. This one happens to be right in the kind of in the sweet spot where we hear very well. And this is where our voices are. Most men's voices and women's voices are either right at this or a little bit lower for men, a little bit higher for women sometimes. But it's somewhere in that range. My voice happens to be a little bit lower than that. My wife's voice is probably right about there. And this is a single frequency. That's why it kind of sounds like a video game sound. Real sounds are mixtures of frequencies. So a piano, when you play a key on a piano, you don't get one frequency, you get a mixture of about 50 different frequencies. And that's why it has more character to it. It sounds more interesting than this just right thing. This is very boring. Let's do, so I can actually add some more tones in here, and you can hear what it sounds like if you just add a few more frequencies. So this is the same frequency. Can you hear how it has a very different character to it? It has a little bit of vibration going on there. This is kind of a representation of the different frequencies maybe that they're adding in here. But it feels more full. It feels just more interesting, more real maybe, right? You can actually, this is actually how they make, how they make synthetic instruments with electronics. They start with a basic tone that is the tone they're looking for, and then they add overtones. They look at the different frequencies that are in a piano when it plays, and they try to add those same ones, and they can actually make it sound just like a piano, or very close to it. So that's how they synthesize music, in other words. So let's do 20,000 hertz really quick. See what that sounds like.
Guys, have you ever thought I can lose weight if someone cooked for me and told me what to eat every day? Well, now you...
Can anybody hear it? I'm pretty sure I can't hear that sound anyway. I'm getting too old. Let's try 15,000 instead of 20,000. Let's try 10,000. Try 14,000. Can you hear it? See, I can't hear that. As you get older, you can't hear these things anymore. Is that really annoying? Okay, sorry. As you get older, you lose those high frequencies generally. And that's just the way it is. It has to do with the flexibility of your eardrums and the movement of your bones. As you get older, things just become less flexible and they can't move as quick, so they can't keep up with this. Right? I used to be able to hear up above 20,000 hertz when I was a teenager and in my 20s. But right around your 30s, it starts to drop off a little bit. In your 40s, as you get close to 50, it really starts to drop off. So, and it's not that you're going deaf, really. It's just that that high frequency end is just dropping out. And so it's unfortunate. What does? It kind of does, but it kind of doesn't too. You know, some things are just not as annoying to you anymore. High screechy sounds. If you have any dogs, yappy dogs or cats, you don't have to deal with that anymore. Then you just wear hearing aids and turn them off when you don't want to listen to people. I'm looking forward to that actually. Because my grandpa did it all the time. My grandpa would yawn and reach up to his head and turn his hearing aids off without anybody noticing. And then he'd just sit there nodding at everybody, pretending that he was part of the conversation. It's pretty funny. Generally, smaller objects make higher frequency sounds because they can. They can move faster. So you have a speaker that has a small cone in it. It can move very, very quickly. And the big cone in it that can't move as quickly makes the bigger sounds. And that's useful too because the middle range stuff is usually the stuff that we hear very well, but high frequency stuff has a tendency to kind of pierce the ear, right? So you don't ever want that high frequency stuff to be really, really loud. You don't want it to move a lot. And so you just make it really tiny and make it move really fast, but doesn't move. It doesn't have a lot of back and forth movement, but it vibrates back and forth very quickly. But the big ones can really move in and out really, really a lot. And you send different frequencies. You send some of the high frequencies up here and most of the low frequencies down, or all the low frequencies down here. And then you kind of mix up in between to cover the middle ground. The little speaker takes some of the middle range, the lower speaker takes some of the middle range, and there's a bit of a crossover. So there's some electronics that are called a crossover when you're building speakers. And that electronics actually, the electronics combined with the actual physical design of the speaker is what makes up most of the cost and the value of a loudspeaker of any kind. So you can buy a cheap speaker at Walmart for I think the most expensive speakers they have at Walmart are a couple $100 for some speakers that you can connect to your television and your whatever and play music. And you can buy one of those speakers that's a Bluetooth speaker for a couple $100 and connect wirelessly to it with your iPhone or whatever. But if you really want sound that is going to reproduce the actual sound that was recorded, it requires a lot of work to get good high quality sound. So in the middle range of good quality sound, you can, well, in the high end of the low end range, you can spend, for example, you can buy Bose speakers or Bose headphones, for example, for a couple $100, $1,000 at most. For kind of middle range stuff, for like a Klipsch speaker or a Boston Acoustics, you can spend $1,000 to a couple $1,000 for speakers, and then you can go crazy. For people that are absolutely audiophiles, they'll do something like go to this company. I've actually toured this company because it was their factory and their showroom and their research lab was right across the street from where I lived, and I went on a tour there. But this is the best speaker company on the planet, without a doubt. They have no competitors really, and their most expensive speakers are like $500,000 each. I don't know if it's this one or this one. I think it's this one that's the most expensive one. And you can't even look at the prices online. You have to actually go into a studio and kind of negotiate the price, because they don't just sell them to you. You put them in the back of your car and take them home. They sell them to you, and then they come to your home. They bring them to your home and they set them up in a studio. You don't just put these in your living room and watch movies with them. These are for people who sit in a room to listen to music from a 40 or 50-year-old vinyl record that was pressed. It was a first pressing of Miles Davis or something, that you can only hear this concert through this record if you want to hear all the great things that happened at that concert, something like that, or that recording or whatever. And it's really, you'd think, why would you pay that much for that? It really is a fantastic experience. I listened to some beautiful music, some beautiful recordings, some old blues. And if you've ever listened to blues live with a guitar player, while they're sliding their fingers across those metal strings on their guitar, there's this kind of little that happens between notes as they slide their fingers on the guitar. That is erased in almost every speaker that is on the earth today. On these speakers, you could feel every ridge of his finger as it passed over every ridge on the metal string. You could feel it coming through the speaker. It was so amazing. And the sounds, it reproduced every sound. But how do they do it? They have all these different speakers that are all custom made. Some of them different. I mean, probably 5 different companies that they've contracted to make these different drivers, that actually make these are called the drivers, these cones. This one right here has a titanium, just a little titanium thing on it. This one up here is made of some composite material. This one here is made of some other thing. And each one of these is fitted to this box that resonates the sound perfectly for that speaker. And the box is made of a material, they won't even tell you what it is, because they invented it just for making speakers. The inside of the box has all kinds of shapes in it that help the resonance, and they won't tell you what that is either, so you have to buy the speaker and break it open if you want to know. And who's going to spend $500,000 on speakers and break them open? And then one of the biggest things that they do is the electronics on the back of their speaker. The electronics on the back of their speaker, which are the crossovers, that's completely top secret. They don't tell you anything about them. But they mix the sound between the speakers so it's absolutely perfect, so that you get a perfect sound thing. And then, of course, all the angles and the directions that these speakers are pointing can be changed to make the perfect experience. And it all has to do with those waves and how they're going to resonate, how they're going to overlap with each other, how these things move within here to create those vibrations. It's all extremely important to make the sound just right. Here they mentioned something that I haven't really mentioned explicitly, and that is, as the frequency goes up, the wavelength goes down. So high frequency waves of sound have small wavelengths of sound. The wave is very small. and low frequency, small frequency sounds have big wavelengths. And one of the ways that you can really see that I think is quite interesting, is in organs. And we'll look at that in just a second. So here we have, here's an example. We're going to calculate the lengths of two different waves. We're going to calculate the length of 20 hertz, which is the low one, and the 20,000, which is the really high one. So we'll start by calculating the velocity of sound in air. They go ahead and do that. It's 348 air at room temperature. 348.7 meters per second at 25 degrees Celsius. Or is it 30 degrees Celsius? So this is warm air. But then we're going to calculate the wavelength by taking the velocity divided by the frequency. So the 20 hertz gives us a 17 meter wave. That's like 50 feet long. And we can hear that, kind of. But at the other end, 20,000 hertz, you get 1.7 centimeters. That's like, the width of your thumb. And that fits in your ear. That makes sense. You could hear that. But a 50-foot long wave, how do we hear that? Well, hearing's an amazing thing. So with organ pipes, an organ pipe has to be about the same length-ish as the wave that it creates. And we'll learn a little bit more about that here in a minute. But if you've ever been in a big cathedral or some church of some kind, you see this huge organ with all these pipes. Yeah, like, let's say, for example, you see something like this one here, right? The biggest pipes that you're seeing here are easily 50 feet tall. These are chairs down here, easily 50 feet tall. And believe it or not, these are not even the biggest pipes on the organ. The biggest pipes are actually laying down behind the organ on the ground. And the smallest pipes are like the size of your thumb, 1.7 centimeters-ish, about that. And you can see those in a picture like this, where they really zoom in on the tiniest pipes in the organ. You can see these tiny, tiny pipes in here that are really, really kind of just minuscule. Here's a great picture of some minuscule pipes in the organ. Right? And I actually bought some pipes, some organ pipes when I was in Omaha. So organ pipes come in all kinds of shapes and sizes and materials, because each shape and each size and each material gives you a different characteristic set of frequencies that make a different tone. This is one of the types of pipes that's in an organ. It's just made of wood. It's just a square box. And it has this little plunger in the end of it that changes the length of the pipe. The further you push this in, the higher it gets. The more you pull it out, the lower it gets. And if you pull it all the way out, you get something completely different. So if I just put it just in the end, just barely like that, and I'm going to cover the end and blow on it because the end has lead on it for sealing. You don't want to blow on, don't want lead in my mouth. So that's that sound. If I push it in more, if I push this plunger in more and make it shorter, it goes up higher. And then if I take that out completely, something really interesting happens. It goes way up by taking it out completely. And I can actually get a really low sound out of it too if I'm careful, if I think I can. Oh, no, I can't. But we'll learn why that is. It's quite interesting, and it's all in the science of these waves and how they resonate in here. And they actually use this plunger to tune it, to tune the organ. So if this note's off a little bit, they just come in here and move this around a little bit and make it in tune. I bought a bunch of those, actually. I want to get some big ones. These ones cost me $5 a piece. The big ones cost like $100, and I just need to find somebody that's selling them. Need some metal ones too. Anyway, so that gives you kind of an idea of the wavelength of the waves that we can hear. It's a huge range of wavelengths that we can hear. What time is it? 5 o'clock already? Holy moly. I need to move quicker. Okay, so intensity. Intensity is a way of measuring how loud a sound is. It's more like how much energy is hitting your ear with that pressure that's hitting your ear. And intensity is equal to power over area. So how much power is reaching your ear divided by the area of your ear would be the intensity. And you can think of intensity as loudness, or the kind of the amplitude of the wave from the center of the wave to the top, or the center of the wave to the bottom. So this would be a high this would have a high amplitude. This would be a low amplitude. And if you have this big amplitude over a small area, you get a huge intensity. And if you get this small amplitude over a small area, you can get a big intensity as well. Because intensity depends both on power and area, and the power is directly related to this. It's actually the square of this. In the end, though, the range of intensities that we can detect with our ears is actually also really, really big. We can detect with our ears an intensity of 1 times 10 to the minus 12 watts per meter squared. That's a tiny amount of intensity. That's the smallest, quietest sound that you ever hear if you just stop talking. Some of those quietest sounds that you hear in a quiet room are at intensities very close to 10 to the minus 12. Very, very tiny. But the loudest thing that we can hear without hurting our ears is 10 to the 12 times bigger than that. 10 to the 14 even. A jet engine you can listen to for a short amount of time, just a couple of seconds without damaging your ears. And it's 10 to the 2. It's 100 watts per meter squared. Where this is 10 to the minus 12 watts per meter squared. That's a huge range. Right? An insane range. And that's actually due to a lot of things. It's due to, in part, the shape of our ear and our eardrums and the liquids inside of our eardrums and the little bones in there and how they interact with the nerve has a lot to do with the nerve itself and how the brain interprets the signals off of the nerve. There's a lot of things involved that allow us to hear this huge range. But we don't want to use numbers like this. This is just an insane range of numbers to mess with. And it is definitely logarithmic. This is 10 to the minus 12, 10 to the minus 11. This one's 10 times bigger than this one. This one's 10 times bigger than this one. This one's 10 times bigger than this one, right? Each time you take a step down, it's 10 times bigger, right? It's like saying, well, do you want 1 cookie or do you want 10 cookies or do you want 100 cookies or do you want 1,000 cookies? You've only gone 4 steps and you've gone from 1 cookie to 1,000 cookies, right? So what we do is we use a logarithmic scale. Instead of talking about intensity, we talk about what we call intensity level, or dB. So when you hear somebody say 50 dB, they're talking about sound intensity level, and you calculate that by using a logarithm of the intensity of the sound you're hearing divided by the lowest intensity we can hear, and then you multiply by 10. So at 0 dB, that's where we start hearing things, 0 dB. At 10 dB, we can hear the rustle of leaves. At 60 dB, that's like a normal conversation. At 100 dB, that's a really noisy thing, noisy factory, sirens, loud, the middle of a loud storm, crazy things like that. Then up here at 140, that's that jet engine. Your eardrums burst at 160 dB, right? And not a good thing. Your eardrums burst when the pressure coming in is so strong that it actually rips your eardrum. So it actually rips through the eardrum, and that's not good. So here we're gonna calculate some sound level. Yeah. Before we do that, let's look at this chart here. Because this is a logarithmic chart, it's not something that scales very easily for us naturally. For example, you don't say, well, this 100 dB is 10 times louder than 90 dB, so 95 is 5 times less loud than 100. It's just not that way, right? 90 dB is 10 times less sound, less intensity than this one. Every time you go step up, it's 10 times louder. 110 is 10 times louder than 100. Not just a little bit, not 10% louder. It's 10 times louder, right? 10 times more intensity. So if you want to go 5 times louder than 100, it's not 105 because it's not linear. This scale is not linear. You have to go to this scale if you want to go 5 times louder, or 5 times doesn't really translate out to something clean. So if you want to go twice as loud, that's 3 dB more. So twice as loud as 100 is 103. Or yeah, it's 103. That's twice as loud. If you want, they do have a 5 times as loud. If you want to go 5 times as loud, it's 7 dB difference. So 5 times louder than 100 is 107 dB, not 105 dB. That's 5 times louder. And 10 times louder, of course, is 10 dB. So you just go from 100 to 110 or 90 to 100. So in this example, they show this. In this one, they want us to calculate the sound intensity levels for sound that has a pressure amplitude of 0.656 Pascal. So that's the pressure. We want to know the power or the intensity. The intensity is equal to, according to the previous equation, the pressure squared divided by 2 times the pressure times the velocity squared. You plug that all in to get the intensity. Then you plug that intensity in here to get the dB, to get the sound intensity. So they calculate this one here. Oh, that's actually, the bottom one is not pressure. This one should be rho. This is a typo. I forgot about that. So this bottom P here is not pressure, it's density. So that's the density of air. So when you come down here, they actually did it right here. It's density, not pressure. So you take the pressure they give you, you square it, divide it by 2 times the density of air times the speed of sound in air, and then that will give you the intensity that you plug into the dB equation. Plug in that intensity right here, 5.04 times 10 to the, actually this is not correct, hold on. You plug that in to get I over I right here. So they actually did the math before. It's 5.04 times 10 to the minus 4 divided by this number here, 1 times 10 to the 12. So that's why they get that's why they get number to the 8th power here. So they did the math. You take this number and divide it by 10 to the 12. Essentially add 12 to this number here. So when you add 12 to that number, you get 5.04 times 10 to the 8, and you put it in this equation and solve it. The log base 10 of this number you do with your calculator, it turns out to be 8.7. 10 times 8.7, you get 87. And that means that 87 dB is an intensity that is 5 times than 80 dB, because up here they said that is, oh no, they don't say that up there. But we know that's true because of this chart. So if it has 7 dB greater than 80, then it's 5 times greater sound than 80, 5 times louder. Now here they want to know if 3 dBs really is twice as loud. If you have something that's at some particular sound level, like 50 dB, is 53 dB really twice as loud? So what they do is they take this intensity level 2 over intensity level 1 and they set it equal to 2. That means this intensity is twice as loud as this intensity. And then they plug that into the equation right here, essentially. So they plug it in right there and they get 10 times 0.3, which is 3 dB. So that's just confirming that chart is correct. Now I guarantee you, without a doubt, that some of you are going to struggle to kind of get this done because it's not intuitive. Logarithmic scales are not intuitive to people in general, and that's totally fine. Don't feel bad about that. If you get to it and you can't make it work, send me an email and I will step you through the process again and try to explain it in a different way that makes sense to what you're missing or what you're not getting quite right. It's nothing to be worried about. It is something that is quite difficult for people to grasp. So let's move on to the Doppler effect and sonic booms. Trying to figure out where So the Doppler effect is something that we're all familiar with. It's this sound right here.
I know it's silly.
It
6'5",
is silly.
300 pounds. I ride motorcycles on the weekends, so the
What does it mean when a jet breaks the sound barrier? Can an object actually move faster than the sound it creates? Other in front of the car, the sound waves behind the length, and the higher the observed pitch. So the frequency that someone standing in front of the moving car will hear will be higher than the frequency that the siren is actually emitting.
There's a
What do you
better,
think?
let me find a better example, a slightly better example here.
Okay, Doppler effect.
So that's a sound we're all familiar with. It happens with motorcycles and cars and airplanes. It goes, "Meow." It goes from a high pitch to a low pitch. Why does it do this? It's really quite simple. The sound waves,
The Doppler effect.
as they're leaving the object, that's a funny little scene from the Big Bang Theory. The sound waves, as they're moving away from the object, create these kind of spheres around the object of high pressure. So each one of these circles would be considered a high pressure region in 2 dimensions. In 3 dimensions, it would look more like a sphere. As they're moving away from the object, they're propagating outward, and they are all kind of evenly spaced. And you could actually measure the wavelength by measuring the length between the pressure wave. So the high pressure to high pressure would be the length of the wave. If this was a higher frequency, these would be closer together. If it was a lower frequency, they're further apart. But that's for an object that's not moving. It's just sitting still. So what if the object is now moving? So now we're going to move it from right to left. It starts to catch up to the sound that it's pushing to the left. It's pushing sound out to the left, but it's also moving towards that sound that it's pushing out to the left. So it's catching up to its own sound. And on the right, it's actually leaving that sound behind it. So what's happening? These waves are closer together. That means they're at a higher frequency. These ones are further apart. That means it's a lower frequency. So the frequency in front of the moving car, if you're observing from in front, will sound higher. But as it passes you, you'll be in this region, it'll sound lower. When you're right here, right as it's passing you, the length of this wave is the same as it was when it wasn't moving. So right as it's passing you, you hear the actual frequency that the car is emitting. But before, you hear a higher frequency, a higher sound. After, you hear a lower sound. Beow, higher, lower, right? And this is, what's his name again? Sheldon. So this is Sheldon's joke in his shirt, is the Doppler effect. On either side, it has these lengthening waves, but it doesn't really make that much sense. It should be all closer on this side and further on this side, right? But it's still the Doppler effect in some instances. And that was his joke for his Halloween costume. Nobody got it except the physicists watching the show. Or people who had taken physics classes recently. Of course, it's the same for the other direction. Here they're showing an eyeball because it works for light waves as well as it works for light waves, just like it works for sound waves to an extent. It changes the frequency of the light, but it's very difficult to observe the frequency change with light because the object has to be moving close to the speed of light for it to be observable. And not many objects move that quickly. But if this was an ear, then we would be hearing that higher frequency as it came towards us and that lower frequency as it moved away from us. It's even true if if the observer is moving. So if the car is sitting still and they've got their horn going and you go past it in a moving car, you'll hear the same thing. As you're moving towards it, it'll be higher. As you're moving away from it, it'll be lower. Right? So it even works for that. It even works if both objects are moving. And this is called the Doppler effect. It's this change in frequency dependent on relative motion of objects. And we can actually calculate it. If you are the object, if you are the observer and you're standing still, then this equation will calculate the frequency that you are observing as the car comes towards you or goes away from you. Okay, so you put in the frequency of Fs is the frequency of the source. So that's the frequency of the object that's making the sound. And then this is the velocity of sound. VW is the velocity of sound. Velocity of wave is what they're using. It's a little confusing, but you need to read down here to make sure you get it right. And then down here you have the velocity of the wave plus or minus the velocity of sound. So the minus sign is used for motion when it's coming towards you, and the plus sign is when it's moving away from you. So you have to read the paragraph underneath to get this equation right. But if you use that equation correctly, you can calculate the frequency that you will hear as it's coming towards you or as it's going away from you. Of course, as it's just moving by you, you hear the actual frequency. If you're the thing moving, if you're the one moving, and the sound source is sitting still, then you use this equation. And you can see it's similar but different. And it has a different way that you use the plus and minus signs too, so you have to be aware of that. The plus sign is motion toward, and minus sign is motion away from the source there. And here they calculate the train horn that has a 150 hertz frequency. It's moving at 35 meters per second, and the speed of sound is 340 meters per second. So you're going to use that equation, that first equation, to calculate the sound that you hear as it's coming towards you first. And we plug in the correct numbers, and we use the correct sign. Coming towards you is minus for this. So we get a frequency of 167 hertz. The actual frequency was 150. We hear 167. That's a higher frequency, which is a higher tone. As it's going away from us, we use the other equation. Sorry, we use the other sign in the same equation because we're still standing still. And it actually goes down to 136 hertz. So when it's coming towards you, it goes up by 17, but as it's going away from you, it goes down by 14. So the change is not the same. Both times it changes, but it changes by different amounts, right? One of them it goes up, one of them it goes down. As it's going down, it goes down less. So that's how you use that equation. The other equation, of course, is if the train was moving through the station and there was a horn going in the station, and you're listening to the horn as you go through the station. That would be that kind of a situation. But what happens if you get a situation where the velocity of the observer, or the velocity of the source of the sound is actually faster than the velocity of the wave of the sound? You get a kind of a strange situation, and this doesn't really work anymore. It kind of breaks this. But that is what happens when you break the speed of sound. In other words, when a jet goes faster than sound, it's not just catching up with its sound, it gets ahead of its own sound. It can actually leave all of its sound behind. And it's the same kind of thing that you see when you're excuse me, in a boat. So when you're in a boat, the propeller of your boat makes a wake behind it because the propeller is creating this vibration in the water, which creates waves that are moving out in the water, but the waves are not moving very quickly in the water. The boat is moving much faster than the waves, and in fact, here we have ducks. The ducks are moving more quickly than the waves that they're making with their feet, right? So what happens is their waves are left far behind them, and each one of these waves is a circular wave that's moving outward, but it's completely behind the duck. See if I can get my drawing tool here. So this is what the little circular waves behind, and you can see the edges of the circle right here. These circles look kind of like this from these waves, moving further and further back behind the ducks from the waves that their feet are making. This is the wave that it just made with its feet. This is the wave that it made a few seconds ago with its feet. It's expanded outward more. And each one of these waves, the edge of them creates this big ripple in the water because they're stacking up on top of each other. Because there's more of these waves. There's another one right in here, that's stacking up, and there's another one right in here that's stacking up. And you can see how they all kind of stack up on these edges. You get all this stacked wave action, and it creates that big wake-like thing on the edge of the, each one of these, as they pile on top of each other, makes that wake bigger and bigger and bigger. If you do this, if you do this with sound, so now let's say that we have this, let's say that this is an airplane and it's making sound, and it gets ahead of its own sound, then you have a sound wave that builds up on top of itself. All these edges that are building, that are stacking up on top of each other, are a bigger and bigger and bigger sound wave that's traveling behind the airplane. And that's what's happening when you break the speed of sound. In fact, right before you get to that point, is even more interesting. Let's see if we, I don't know if they have a, doesn't look like they have one. Let's see. So here is a simulation we can use. We have this is our airplane that's going to be moving. We'll let it go. And you can see that it's almost catching up to its sound. It's almost going as fast as its sound, the sound waves it's making. But you can see that it's building up this huge barrier of sound in front of it. And that's what is the sound barrier. Each one of these lines represents air pressure. And it's hard to push the plane through air pressure. As you push through the air pressure, the pressure hits the wings, and if it doesn't hit it just right, it can cause turbulence on the wings and the plane to crash. And in fact, that's exactly what happened to everybody who tried to break the sound barriers. Their plane crashed, and pretty much all of them died. It wasn't until one particular pilot came along. His name was Chuck Yeager, and Chuck Yeager, to put it plainly, was just a badass. He actually broke through the sound barrier and lost control of his plane and almost crashed. Broke his helmet, broke his canopy with his helmet, and he did all of this with a dislocated shoulder because he'd gone riding with his wife in the desert the night before on a horse, and he was drunk and he fell off the horse. And he didn't want to tell anybody because he didn't want anybody to know. He didn't want anybody to take him off this flight. He wanted to be the one to break the sound barrier. So he did it anyway, and he survived. He actually lost control of his plane, regained control, pulled out of the crazy spin that he was in, and survived the flight and broke the sound barrier, and went on to do all kinds of other things. My favorite thing that he did was he flew a plane into outer space. They actually built a jet plane that had an engine that was like 10 times bigger than anything that's ever been put on a jet plane before. And then they put a rocket on it. They just welded a rocket on the back of it too. And so he took this plane and he just flew it straight up into the space. And when he ran out of jet fuel, he turned on the rocket and kept going. And then he ran out of the rocket fuel and he couldn't control the plane anymore, and it lost all power, and he just fell back down to earth. And he tried to control the plane, couldn't do it. And so he finally ejected like 3,000 feet from the ground, going like 1,000 miles an hour. And his helmet was on fire. Inside his helmet was on fire, like his hair was on fire. And he couldn't take his helmet off. And he landed on top of his burning plane. And he broke like both his legs and an arm. And he walked out carrying his parachute in his helmet. He was just the craziest person on the planet who ever lived. But that was Chuck Yeager. It's a great read one of his biographies. He's a great life. He died a couple years ago, but lived a great life. But anyway, he was also the only person in U.S. history to ever become an ace in one day. In one mission, he shot down 5 planes in World War II. In one mission, the only person to ever do that. So, anyway, the point being, if we go faster than the speed of light, right now we're going faster than the speed of sound. Right now we're going slightly slower than the speed of sound. But if we increase our speed to faster than the speed of sound, then we're going to get a completely different situation where, whoops, that's not what we want to do. We want to reset this. How do we reset this? Reset, there we go. Nope. Reset. Velocity of source, there we go. So now this plane is going faster than the sound it's making, and you can see that all this sound is piling up behind it, and that's a wake, like the wake of a boat. It's called the sonic boom. That particular wake is called the sonic boom. It's a big wall of pressure that when it hits the ground, it's still stacked on top of itself here. And you can hear that boom on the ground. And when Chuck Yeager broke the speed of sound the first time, they heard a boom. And it was this, but they didn't know what it was. They didn't know that was going to happen. And so they just thought, oh, he must have died because he must have crashed because that's happened to everybody else. But then they saw his plane flying by again. And they're like, oh, he's still alive. So, anyway, speed of sound and the Doppler effect and all that. Now, sound interference and resonance. This here is kind of the crux of the chapter, the big deal of the chapter. I've already talked about hearing a fair amount. Ultrasound I've talked about a little bit. But this one here, sound interference and columns, this is where we talk about how we resonate sound to make it beautiful or to make it something we can hear or something else like that. When you have constructive interference with sound, the waves pile up on each other and it gets louder. When you have destructive interference with sound, the waves and troughs cancel each other out and you get less sound. Usually with music, you want more sound. You want to resonate with those frequencies, resonate with those waves. And so how do we do that? So if we take a tube, just a tube of whatever, cardboard, and we take a tuning fork and we hit it on something and hold it next to that tube, if we get the wave from this tuning fork matched up so that it will fit inside this tube just right, we can actually make it resonate in the tube. And it's an experiment that we could do with the equipment I have in this room, but it's not something that I can send home with you because it's quite large. I just found some equipment that I can send home, but I haven't purchased it yet. But anyway, you can do this with water glasses and put water in them and use a tuning fork if you have a tuning fork, or you can use a speaker if you need to. But it can be done lots of different ways. The kid that broke the glass did it by finding the tone that when he sang it made that straw move because it was making the glass vibrate. But if you remember, it also sounded like it was louder because it was actually resonating in the cup and coming out of the cup amplified. You also notice this if you're in a bathroom and you're singing to yourself. You'll find that there are certain notes that sound louder. You can actually find a note by going ooh, and suddenly one will just bloom and get louder for some reason. And that's when the wavelength of your wave is fitting in that room just perfectly. So when it bounces off one wall, it bounces back on top of itself so that the peaks are on the peaks and the troughs are on the troughs, and it makes them bigger. And that's the idea of the resonance. So we need to find that situation that happens with tubes. If the tube is open on one end, the wave is just going to go out the other end and not really bounce around much. But if it's closed on one end, it will bounce back. So we'll start off with the one that's closed on one end. You have a wave that goes down from one end and bounces back the other end, and we want the wave to build on itself. So we're gonna represent it using this transverse wave, which represents the pressure. This is gonna actually represent the movement of the air. So at the end of the tube, the air doesn't move at all because it can't move. It's running into a wall. But at the end where it's open, it can move around because the air can go out of the tube and you can suck air into the tube, and the air can move a lot there. So this movement of air represents the wave of sound, and the longest wave that we can fit into this tube is actually just a quarter of a wave, where it's not moving here and it is moving here. This is the representation of the wave, and they show it going up and down, but it doesn't matter. But this is only part of the wave. This wave is actually 3 times longer than the tube. You can see here, this is split this one in two, split this one in two, they'd all fit into this tube. So we're essentially fitting 1/4 of this sound wave into this tube, And as it comes down here and comes back, it will build on itself because it's lined back up with where it can move and where it can't move. Right? What we normally do for this is we cut a tiny little hole one end and we put the sound in there. That's why organ pipes have this little hole here. This is called the FIP. And as the air comes from the pipe on the bottom, it moves past the FIP and creates a little wave. It creates a little disturbance, and that's what creates the wave that bounces back and forth. And this is a closed-end pipe right here. Closed-end pipes can create very long waves in a very short space because you can fit a quarter of a wave in there and it will resonate with that wave that is actually 4 times bigger than that quarter of a wave you fit into it. And that's why when I put this thing in and blow through it, I get a low tone, but when I pull it out, it's much higher. It can't resonate with that low one anymore. It resonates with a higher one, and we'll see why that is here in a second. It turns out that if you have a closed-end tube, you can also fit a wave in that doesn't move at one end and does at the other if you put 3/4 of the wave in. 1/2 the wave won't fit in. If you try to fit half of the wave in, it won't be moving at both ends. But at this end, we know it moves. And at this end, we know it doesn't. So we have to go to a place where it's going to move on one end and not move on the other. So we go all the way out to here. 3/4 of the wave can also fit in that tube and resonate. So we're going to get this wave in this tube, this really long one, and we're going to get this one that's a bit shorter as well. It's just a little bit longer than the length of the tube. And in fact, you can fit that really long one in and that 3/4 one in, and you can also fit one that fits entirely in the tube plus a little bit. And you can fit one that fits in the tube 1 3/4 times also. And it goes on, you can fit more and more in there. And these are called the overtones of that closed-end tube. For a particular tube of length L, you can fit in a wavelength that is 4 times the length of the tube, one that is 4/3 times the length of the tube, one that is 4/5 times the length of the tube, one that is 4/7 times the length of the tube, one that is 4/9 times the length of the tube, and so on. And you can fit all those frequencies in there. And those are all the overtones of a tube that is essentially a cylinder with a wave coming in and it's blocked off on one end. Those are all the overtones. This first one is called the fundamental. This is called the first overtone, second overtone, third overtone, and so on. And there's an equation where we can calculate that, and it's right here. They actually go through how that would be calculated, and this is what it looks like. This formula tells you all the different wavelengths that can fit in there. You take the velocity of the wave, you divide it by 4 times the length of the tube, and multiply it by the number of the overtone you want. And the number of the overtones are 1, 3, 5, 7, 9 for the closed-end tube. So for the fundamental, you plug in 1. For the first overtone, you plug in 3. For the second overtone, you plug in 5, and so on forever. Closed-end tube has that property. Our voices are like a closed-end organ pipe. We have this thing vibrating down in our throat, our vocal cords, and our mouth is open when we speak, so that's the open end of the tube. The throat is the closed end of the tube. Air can't really go anywhere down there, but it can go in somewhere on the end, at the end of our mouth. So we're a closed-end tube. We're not a cylindrical closed-end tube, and we're also not a straight closed-end tube. So we have a different quality than an organ pipe when we speak. But there are organ pipes that are designed to sound more like voices. And how do they do it? They shape it like our throat, and they even bend them. So they look like a human throat and mouth and everything. And those tubes, when they play them on an organ, sound like voices singing. Or somewhat like voices singing. They also make them out of different materials. So here we're going to find the length of a tube that has a fundamental at 128 hertz. We're going to use this equation. We're going to use this number, will be 128 hertz. We're going to use the fundamental, so n will equal 1. And the velocity of sound is going to be 331 meters per second. We plug all those numbers in, solve for the length of the tube, and we get the length of the tube is 0.672 meters. So about a half a meter, about 2 feet. In part B, they want us to do the frequency of its fourth overtone. So to find the frequency of the fourth overtone, we just found the length. We plug in the length, the velocity, and the fourth overtone would be n equals 3, 5, 7, 9. That would be the fourth one. So we plug in n equals 9, calculate that frequency, and that's what they do here in part B. plug in 9, 1.15 kilohertz. What if it's open at both ends? What if both ends of the tube are open to the air and then you put a sound in it? Well, if you do that, both ends have to have moving air. So the smallest wave we'll be able to fit in there is a wave that's moving on one end and moving on the other end, and somewhere in the middle it's not moving at all. Because if it's waving back and forth on this end, the other end is going to be moving back and forth in the opposite direction. That's just the way it is. So it has to be going through a zero movement spot somewhere in the middle. And I don't like it when they show it doing this, because I prefer it to be just going from here to here, but whatever, that's their choice. But the next overtone that will do that will be one that's open at this end, then goes through two. These are called nodes. So it goes through two nodes in the middle and then opens again. And the next one goes through 3 nodes and then opens again, and then 4 nodes. And this one actually has an equation for it as well. And it's similar to the other one. It's n times the velocity of the wave over 2 times the length. And the n is now equal to 1, 2, 3, 4, 5, 6, 7, 8 instead of just the odd numbers. And so but it's the same kind of thing. And that actually does conform to certain instruments. They actually do have open-ended organ pipes. So the open-ended organ pipe, you have movement at this end because that's where the air is coming in and it can move. And you have movement at this end because it's open to the thing. But also trumpets are that way, clarinets are that way, tubas are that way. Most wind instruments are open-end. But their overtones don't exactly match these ones here, because different shapes change the overtones as well, and they change the loudness of the overtones. If you have a trumpet that starts off with a small pipe and ends with a big pipe, a fairly big pipe, it actually allows some overtones to be louder than others, and so it changes the mixture of things, and it changes the overall sound. We call that the timbre of the instrument. Drums, like these drums, right? This thing here, you hit this bar and it vibrates, and then it resonates in these little things down here. So this is kind of like a marimba or something. But actually, they call it a marimba. They're using these gourds in it, but these are closed-ended chambers, right? But there are also marimbas that have open-ended tubes where the sound goes in one end and comes out the other as well. So it has a completely different sound. Different sets of harmonics or overtones or whatever else. So here they talk about pitch, which is the frequency, so how high it is. The higher frequencies, higher pitch, higher sounding notes or sounds. Loudness is intensity and frequency. The timbre is all about those overtones, the mixtures of overtones, how loud they are, which frequencies they are. That creates the timbre, or the quality of the sound, or how different it sounds from other sounds, that kind of thing. Note is similar to pitch. It's just the way we talk about it in music. And then tone is actually also very related to timbre. Same thing there. And here they talk about how well we hear different frequencies. So different frequencies sound louder to us because of our physiology and the connection with our brains and all these things. And this chart kind of is a way of showing that. I don't like to go through it because it's really confusing, and I don't really use it anywhere. I don't think I've given you any problem with that. Here they do an example of it, but I don't think I put it in the homework at all, so shouldn't have to deal with it. Here they talk about how the whole hearing mechanisms works with all the little bones inside, but we already talked about that a bit. Here it's a little more, this is kind of like a free body diagram of that, but again, we don't really do anything with it that much, physics-wise. Ultrasound is kind of like the idea with the bats, where we send a sound out and then we wait for it to bounce off things and come back to us and listen to it. But we're sending it out with an electronic transmitter, and then we're receiving it with a microphone that listens to ultrasound. Ultrasound is frequencies that are above the frequencies we can hear. So above 20,000 hertz is ultrasound. And those higher frequencies can penetrate liquids and solids better than the frequencies we hear can. So as they penetrate things, they go through and they bounce off of different things. When they bounce off something soft, you get a different bounce than when you bounce off something hard, for example. And this is actually the reason that they have to put the goop on you when they use an ultrasound. If you're doing an ultrasound, they have to put this gel on you, because if they don't, the sound will bounce off your skin and go right back into the ultrasound. So they put the goop on there so that the sound travels through the goop and through your skin and through the amniotic fluid or whatever it is they're looking at. And then when it encounters something different, like the skull of the baby or the organs of the baby, that's very different than the water that they're sitting in, then it sends back a different sound. And that different sound comes back to the transmitter, or to the receiver that's built into the transmitter usually, and that is sent to a computer to create an image. So those different sounds are processed to make an image. And this is actually a fairly old-fashioned kind of image. You can do three-dimensional ultrasounds now with much higher resolution. So here they show the transmitter, and they can even see the kind of goopiness on the belly with it's kind of shiny right there because they put that gel on there. It's usually like KY jelly or something similar. But you can see here there's a lot more detail in some of these. You can see ribs. You can usually see one of the things they're looking for is they're looking at the spine and how it's developed, and they're looking at the brain cavity. They're looking at the heart to make sure there's no heart defects. They can actually look at blood flow and electrical things as well using this. They get some different things, but then they can go in and do high resolution three-dimensional ultrasound. So you can actually see the surface of the baby's face. You can see the baby's body. You can look for higher resolution things like spina bifida, which is parts of the body that are open near the spine, which causes some serious problems. So, but you can also look at different organs in the body using ultrasound and things like that. So, ultrasound is getting quite good at seeing soft tissue things inside the body by bouncing sound off them and processing that signal with a computer. And that's the end of this chapter for you. I am going to turn you loose. It's the longest day we've had since the first day, I think. Have a great evening, and we'll. Don't forget to send me or to bring me your lab kits when you're done with them, and also don't forget to make an appointment to do your finals. If you have any questions about the homework, please contact me as quickly as you can, so we can make sure you crank all that out. Any other questions or issues or problems or concerns, please contact me as soon as possible. Make sure we get everything all wrapped up for the end of the semester. And thank you for taking my course. I enjoyed teaching. I enjoyed teaching you all. I enjoyed interacting with you all. I hope you have the rest of your summer. If you're interested in taking the second half of this class this coming semester, make sure you contact me as well with that information. And maybe we'll see you again. Best of luck to all of you in your future endeavors. Have a good one. Now I've got to stop my recording here. I can't. Can't see the top of my screen at the same time. Thanks for joining me on the last day. Oh, it's just plug it into your calculator. So if you're taking the logarithm of 5, for example, you just press, what kind of calculator are you using? Is it a Texas Instruments? It's a Casio. Oh, Casio, okay. So, yeah, I'd imagine it's the same. Just go ahead and press the log button. And you usually have two. You usually have a LOG and an LN button. The LOG is the one that you want.
Okay, let's see that.
Let's
Oh,
see.
it's this. Is it this
Yeah,
guy?
that's that.
Or is this guy?
It's the,
So maybe that explain. I was trying to follow along in 17.3 and we were doing the 10 times log to whatever, but
let's test it. The log base 10 of 10 should be, should be 1. So that's right. So whatever you just
is
did.
it automatically 10? So I don't
So,
have to
so
put
did
10
so
or
did
10?
you use this button or this button?
I used this button.
Yeah, so it's automatically 10.
Okay.
So if you do shift log and then whatever your number is, if you end up with 5 in there, for example, then you would go ahead and do that, press equals, and it gives you points.
Okay.
So it's that, just like that.
So I don't have to type 10
Nope.
log.
Well, you still have to multiply that by 10 because in the equation it says 10 times the log base 10, right?
Yeah.
So you still would have to multiply that by 10.
Could you bring that equation up real quick? Because I think I was getting something a little funky. I just want to make sure. This is a 17.3.
Yeah, so in this equation you have the intensity that's inside the log.
Yep.
You have to calculate that ratio first, and then you take the log of that, and then you multiply it by 10, and that gives you the dB. The
Okay.
decibels.
So if I was going to do this guy down here, if you, wherever it was at, it was like times 5.04 times 10 to the 8.
This one right here.
Yeah, there you go.
Go ahead and do it. So you just do, you could do it a couple of different ways. You could actually do 10 times log of 5.04 times 10 to the 8.
So like that, right?
You could do that, yeah. Hit enter. What did it give you? 87?
No, 5. Whatever that is.
Oh. So 10 times, I think you have to put a times in there.
Okay.
And then
log.
shift log 5.04 times 10 to the 8, and then close that parentheses, and then hit equals 87.
Okay, that's where I was getting it wrong. I was putting 10 log 10
Yeah.
times.
Yeah, I definitely want to do 10 times log, and that log is already base 10.
Got it. That makes sense.
Okay.
Okay, awesome.
All right.
Cool. Thanks.
Yep, no problem.
You were saying something earlier. It kind of reminded me of something that I heard before. A lot of the Air Force pilots like to do flybys on the towers.
Uh-huh.